My name is Peter Swedlund. I am a chemist. I teach chemistry at the University of Auckland. Actually, to be honest, I only really feel like I got into science, really enjoyed it once I'd started university. At school, actually, I thought it was pretty boring, to be honest. Yeah, I think it depends. I mean, mathematics is a tool. I mean, for me, it helps you understand, your results. It helps you understand the relationships between variables, and within chemistry, I mean, there is an enormous spectrum of the amount of mathematics that you would need. I mean, from some parts of chemistry, you're just interested in how do you make a certain compound and knowing what products you get from a certain reaction. And you wouldn't need to have a very complex understanding of mathematics and other aspects of chemistry. Then you would quite literally need to have a very deep understanding of even complex numbers. And I do think that having maths in your vocabulary whatever you're doing in science, it will help you more deeply appreciate it. I suppose one of the things which surprises me quite frequently is when you are trying to understand something, whether it's about a molecular structure, how you need to revert to maths that you learned at high school. Right? We use trigonometry all the time. It's surprising. And basic geometry and trigonometry comes up all the time. Yeah, absolutely. I think, I mean, for me anyway, I would spend a reasonable amount of my time, well, not a measurable amount of my time, trying to develop my insights into understanding the numbers that I'm working with. So I mean, I do a lot of physical chemistry. We measure spectra, we measure rates of reactions, and we're frequently looking at structures, and frequently we are, I am pushing against the limit of my understanding of maths, and that is just something which just continuously evolves. If you just take things as far as you can, push them a little bit beyond, and you keep expanding that that limit. I suppose computers in general can look at things in many dimensions and very rapidly. For me, for example, I end up with maybe 100 spectra, and if you want to compare those, and they might be showing how a system is changing over time. I mean, if you can, for a start, just graph them and look at those spectra and how the shapes evolve over time, and knowing a little bit about the chemistry of the system, it can give you very powerful insights. And even like to look at subtle changes, we would use certain functions within software programs, like just calculating a second derivative of a spectra. You have 100 spectra there. You can basically push a button which says, show me the second derivative, and then suddenly you have a lot more information or a different view of the data, and it is fantastically powerful to be able to use these tools to look at data from lots of different directions, plot different variables against other variables, and then suddenly you see the connections and the interrelatedness that were hidden, unless you could actually visualize the system with some graphical presentation. So we would just sort of like the very first thing you do when you get some data is you plot it up, look at it from all sorts of aspects, look at derivatives, look at Fourier transforms, look at, and it's all just clicking a button. Yeah? You don't sit there with a pen and paper calculating complex derivatives of algebraic formulas. Basically, you click a button and you see you see your data as long as you know what button to click and a few of the variables that are going on in the background, and you can very easily use software to get very powerful insights that would not be wouldn't be obtainable otherwise. Yeah, no, if you look at, for me, for example, where we have spectra, you might have a broad feature and there's lots of overlapping peaks underneath that. And if you can mathematically look at the data so you can see the underlying peaks, and if you take a second derivative, you know that you will see the points of inflection from the definition of a second derivative, that you'll get a maximum at these points of inflection of the negative second derivative. But you don't need to actually mathematically do that each time. You're just clicking a button. As long as you know as long as you know the basic principle. You don't have to know all the details for calculating a second derivative to be able to click that button and see where the points of inflection are. So a spectrum is essentially comes from the word for a ghost. Newton called it a spectrum when he saw the rainbow when white light was refracted through a prism. And so essentially it's measuring some function, typically absorbance of light as a function of the wavelength. So these are some, this is an example of probably 100 spectra measured for different systems where we're measuring absorption in the infrared, so beyond the visible part of the wavelength of the spectrum. We're measuring absorption as a function of wavelength. So in terms of the relationship between theory and practice, they are like, for me anyway, they're very much two sides of the same coin. You can't have a one-sided coin, and I don't really think you can have a full understanding of science purely theoretically without having some understanding about how the theories were developed. I mean, the theories were developed from very practical experiments, from people setting things up with their hands, and that's how they developed the theory. And if you don't have an understanding of, the theory, to me, science is almost the relationship between people and the physical world, and how we understand it. And it is by doing experiments. And if you don't understand the experimental side of it, then you won't fully understand the theoretical side of it, and certainly vice versa. I mean, you can do a fantastic experiment if you don't understand the basic theory underlying what you're seeing, then you will not, you won't understand it. So it is, they go very much hand in hand, in my opinion. My own sort of area of chemistry is to do with sort of geochemistry, chemistry of the earth, but also environmental chemistry and how contaminants behave when they're released into the environment. And it's to do with our society's relationship with the resources that sustain us, the water and the air and the soil. And I think I sort of came, I suppose, into this area of science not as a young person. I suppose if I was probably about 30 before I sort of made the connection between science and society. Essentially, I sort of came into science thinking of it very much as an abstract theoretical construct. And if I was talking to myself as a young person, I would say, you should look at how science, manifests itself in the day-to-day experience of it, and how it improves the ability of a society to use the resources that we have. So when I look at the world, I think my own sort of insights or vision into it. As I said, I'm interested in geochemistry, water, soil, rocks, and there is a fantastic dance that goes on between these systems all the time, and whether it's the insolubility of iron oxides or various other components, the dissolution of silicate minerals that form deep in the ground, and then when they come up and meet water and oxygen, they break down and dissolve, and iron oxides precipitate, and we get soils. And then how the chemistry between the water and the soils influences the way that a tree gets its nutrients from the ground. And to my mind, I am always just amazed at the fact when iron oxides are so soluble, but iron is an essential nutrient. And there is one particular image I have of a plant grown with its roots in agar. And in this agar, so it's transparent, but it has a pH indicator in it. And you see when the plant is deficient in iron, its roots exude very strong acid which solubilizes iron. And so the tree is actually eating the soil, and in response to being iron deficient, it's excreting acids that will dissolve the iron in the soil. And to me, that's you just look at a tree and it's got this fantastic dynamic interaction with its surrounding.
So can you explain what that obelisk is behind you on the shelf?
So speaking of rocks and silicates, this is a natural quartz crystal which would have precipitated either very slow cooling or evaporation of some hot geothermal fluid, and the shape of it tells us about the arrangement of the atoms within the structure. And the angles between the faces tell us about the sort of the bricks, the building blocks, what we would call the unit cell, the shape of the unit cell. And even if you look through it, you can see it's not perfect. It's got lots of inclusions. And if you looked at the nature of what was in the middle of it, it would tell you a lot about the conditions under which this particular crystal grew.
So has that been shaped and polished to have that point on the top?
It's been polished, but the shape is well, I bought this off eBay, and anyone who's interested in minerals, there's many on eBay. And formerly, it has, they're grown naturally. Here's a little cluster of the same basic shapes, and the angles, they're all the same.
It was plain.
No. They grow with this shape because of the shape of the building block, the unit cell.